Hello class, and welcome to today's algebra lesson, which is about scatter plots and lines of fit. By the end of today's lesson, you will be able to create and apply lines of fit, as well as interpret the meaning of the correlation coefficient. So a correlation coefficient is a number that measures how well a particular line fits a set of data. Those lines are called lines of fit. Those are approximate linear equations for the trend of the data. When we were talking about our trends yesterday, we had the clusters, so this would be an example of a positive cluster. A line of fit is saying there is a line that can go through the data, but there could be another line that could go through the data. So there are multiple lines of fit that model the trend. The correlation coefficient helps us decide which one is the best or the closest to the actual line of fit. No scatter plot has one perfect line that connects it. That's why it's a scatter plot. But the correlation coefficient helps us to determine how accurately a linear equation models the data that is being represented. Once we have our line of fit, we can do two things with it. We can do extrapolation, which is plugging in values outside of the data set to help us predict, or we can do interpolation, which is once again helping us predict, but that's within our range of data. So we're going to start by just talking about what the correlation coefficients mean. A perfect correlation, so something that would be in a perfectly straight line and going positive, would have a correlation coefficient of 1.0. On the flip side of that, something that is perfectly negative would have a correlation coefficient of negative 1.0. Everything else falls in between having weak correlation, strong correlation, or no correlation. The no correlation is when we have no trend. There is no cluster of points. When determining whether it's weak or strong, so whether that model fits our data really well because the dots are really close to the line that we would put in, or whether they're a little bit more spread out, is determined kind of by the spread of the data. A general rule of thumb is on the positive side, something is considered weak if the calculated correlation coefficient is below 0.5. It's considered moderate, so the line kind of fits the data from 0.5 up to 0.8. And then it's considered strong or a really good fit for the data if it's anything above 0.8. On the flip side of that, weak would be negative would be taking all of these values and making it negative 0.5, negative 0.5, negative 0.8, and negative 0.8. So it's the same rules when it's on the negative side. So we're going to start by talking about what we have for the lines of fit. So this one is already graphed for us and has a line drawn in. If you are given a set of data that already has it drawn in, your job is to pick 2 points on the line. It is not just 2 random dots, it is 2 dots that hit the line. The other piece is it doesn't have to actually be a dot. It should be what is easiest for us to calculate. So as I start going along, the first point that I encounter here is at 160. So that's going to be the first coordinate pair that I am going to use. Then I keep going. Well, it's hitting these dots. They don't really fall at a nice intersection like 160 did. So I'm going to keep going until I hit another perfect intersection. Even though 6 and 66 is not a dot on the graph, it is a point on the line. And our job right now is to find the linear equation, so something that is occurring on the line. So now I have my 2 points, which means I can find my slope by using x1, y1, and x2, y2. So I'm going to plug it into my slope formula and do 66 minus 60 over 6 minus 1, which is going to give me 6 over 5. When you are doing scatter plots, this is the only time that you are allowed to convert your slope into a decimal. So I'm going to convert this into 1.2. If it gives you a long decimal or a non-terminating decimal, round to 2 decimal places. So in this case, 6 divided by 5 gave me a nice round decimal of 1.2. Then I'm going to go ahead and plug it into point slope formula. So y minus 60 is equal to 1.2 times x minus 1. And then the point of these trend lines is that I want to be able to manipulate them quickly. So I'm actually going to convert my final answer into slope-intercept form. So first I distribute the 1.2 times x, 1.2 times 1. And then I add 60 on both sides of my equation. So my trend line for this particular set of data is going to be y is equal to 1.2x plus 58.8. So we picked some points from the graph, found the slope, wrote it in point slope form, then converted it to slope intercept form. Go ahead and try this one on your own using the 2 points in blue that they give you on the line. So first we calculate our slope. It's going to convert to a decimal that we need to round. So we go to 2 decimal places and get 32.14. Plug it into point slope form. I chose the first point, 250. If you chose the second point, 516. It would still work out to the same final slope intercept equation, which is y is equal to 32.14 minus 14.28. Sometimes the graph is not drawn for us, and we're going to need to go ahead and create it ourselves. When you are doing this, you want to consider the scale of your graph. So on our x-axis, we're counting by 5s, and I want to try and use as much of the graph as I can, going from 35 to 60. So I'm going to use that counting by 5s, and I'm going to spread it out a little bit because we have some space. So I'm going to start at 25, and then I'm going to leave some space and go to 30, 35, 40, 45, oopsies, 45, 50, 55, and 60. So I've used basically the whole graph and my points will be spread out. Then I look at my y values and my lowest one is 3.88. My highest one is 6.75. So we're roughly going from 3 to 7. So I'm just going to round it down and make us go from 1 to 7. Again, leave some space, especially since these are decimals. I'm going to count by ones and leave a space in between for the halves. So half, 1, 1.5, 2, 2.5, 3. Notice, as I'm filling these in, I'm not actually writing on every line. I'm going every other. As long as it is clear what you're counting by, you can skip over and do every other. So then our goal would be that we have to actually plot those points. So once I put those on, it's going to give me a graph that looks like this. Your job then is to put in a line that is going to follow the general trend of this data. In this case, our line is going down. Now, we want a line that actually goes through the data, and we might have to adjust it a little bit. When you're doing this in class, you'll be using a ruler, so you might want to move that around to find an actual good fit. We wouldn't want a line going down like this because that doesn't really touch any of our points. We want to try and get it as close to as many points as we can. It doesn't have to touch any of these points. The more points it touches, the better. But in theory, it technically does not have to touch any of the points. In this case, I've got it going directly through 1, and the other points are almost all very close to the line. This top one is a little bit high. But again, this would be a perfectly fine trend line. Anything, if I tilted it down a little bit, that would still be okay. If I tilted it up a little bit, that would still be okay. But you want it to go basically through the center of your data. The other thing that you want to make sure is when you are putting in these lines that you're going to be able to pick out points that you can calculate. So with this line that I have here, I can look, and as I'm going, I have a first point at 37, and then as I keep moving, I run into another point here, which would be at 47.5, halfway between 45 and 50, and then at 5. So my 2 points here are 37 and 47.5, 5. Again, this is not the only line that we could use. This is just the one that I drew in. So now I'm going to take and I'm going to use my slope formula. So I'm going to take y2, which is 5, minus y1, which is 7, over x2, which is 47.5, minus x1, which is 30, giving me negative 2 over 17.5. When I calculate that slope out, it's going to give me a long decimal, so it's going to be approximately equal to negative 0.11. Then I'm going to go ahead and plug that value into a point slope formula. So y minus 7 is equal to negative 0.11 times x minus 30. Then we want to continue to simplify down to a point slope form. So I'm going to distribute, and I'm going to get negative 0.11x. Negative and a negative makes a positive. 0.11 times 30 is 3.3. And I'm going to finish by adding 7 to both sides, giving me a slope-intercept equation of y is equal to negative 0.11x plus 10.3. Once again, this is not the only line of fit that could go through this data, but all of the lines would be very close to this value. So now that we've calculated our trend line, we can apply that and make some predictions. Remember, there were two types of predictions: extrapolation, going beyond the data, and interpolation, staying within the data. So we're going to start by practicing the extrapolation. So 70 kilobytes per minute is a faster internet speed than we were given in our set of data. So go ahead and plug 70 into your equation and make the prediction. So when we plug that in, we find that if the internet speed is 70 kilobytes per second, it is going to download in 2.3 seconds. Now we're going to do the interpolation, aka calculate for a point within our data. So 42 falls within our set of data, so this is called interpolation. You're going to make the prediction the same way by plugging it into the equation, so go ahead and do that on your own. So we plug that in and we get 5.68 seconds. So now that we've talked about how we find those trend lines, we're going to circle back to this correlation coefficient. So the correlation coefficient tells us how well the line matches. So whether it's a really tight fit to the line or whether it's kind of follows the line but is a lot more spread out. So what does R, which is what stands for the correlation coefficient, of 0.1 mean? That would be a weak, because it is below 0.5, positive, because it is a positive value, correlation. So it is saying there is a little bit of correlation that exists. The line kind of fits the data, but hardly at all. On the flip side of that, if we have R of negative 0.935, that's going to be a strong. It is very close to 1.0. So strong, and then it is negative. So I should have said it's very close to negative 1.0, and then correlation. So that means that the data is very, very close to the line that was drawn. Go ahead and interpret this correlation coefficient on your own. So when we've got R is equal to 0.456, that's right around 0.5, which still gives us a weak positive correlation. It says only about 50% of the data actually lines up with this model. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.